Welcome to my classroom. In this fuel cells and batteries course, we have been discussing about the importance of alternative energy technologies, what is the need for fuel cell technologies, and in the previous lecture, we have discussed about the history of fuel cells. In this lecture number 5, we are going to discuss about classification of fuel cells. Ready? So we should be able to recollect. We have seen that if hydrogen is used, the byproducts are only heat, water vapor, and electricity is a major product, right? But instead of hydrogen, if you are using hydrocarbons, what will happen? There will be products like products which contains C, H, and O, right? So obviously there will be CO2 formation will be there, right? Well, and we should recollect in the previous lecture we have discussed about why fuel cells can replace this diesel generator, mainly because when these diesel generators are operating, they will be making noise. Also they need some time to start, right? It's not like in fuel cell, if you just switch it on, there will be discharge of power, whereas diesel generator, it needs some time to start it and then it start functions, right? So that is what happened. We have witnessed it in our apartments also, right? And similarly, in case of IC engines, its efficiency is limited by Carnot cycle. So can you tell me whether this fuel cells efficiency is affected by Carnot cycle? We'll come to know that. Okay. And whereas in case of fuel cells, it can be kept in near to the remote locations and where the application is there, where the demand of power is there. There itself, these fuel cell generators or fuel cell power units can be kept. So thereby we can avoid the transmission losses. We know that transmission losses is taking place in the electrical lines when it is taken from one location to another location, right? And if it is a steam power plant, a lot of hot water or steam is being generated, and before disposing of the water into the river bodies, we have to cool it down. So large equipments are we need a cooling towers kind of setup. Large space is required, energy is required to cool the water to room temperature and discard it off, right? So in case of fuel cells, we don't come across such issues also. And another advantage with this fuel cell is it can be used in combination or as partial load, right? And we have seen the definition of fuel cell. If you recollect, fuel cell is an electrochemical energy conversion device which can directly convert the chemical energy into electrical energy, right? Another advantage with this fuel cell is it will operate continuously. It will keep on working. Unlike batteries, in batteries a certain amount of chemical energy is kept in the battery. Once it is consumed, so it will stop serving, whereas a fuel cell, it will keep working as long as we supply the hydrogen and oxygen. That is, hydrogen is the fuel, oxygen is the oxidant. So as long as there is supply of this, it will keep working continuously. So and what is the similarity between this fuel cell and batteries? Like batteries, fuel cell also contains 2 electrodes, 1 electrolyte, and this also generates DC power. Battery also same, right? And what is the difference? In case of fuel cells, the active material, that is the hydrogen, oxygen, all that, they are being supplied from outside. Though externally they are kept supplied, whereas in case of battery, these active materials are present inside the battery. Okay, and what about the life? The life of the battery is limited because the amount of active material that is present inside the battery, once it is exhausted, so its service is stopped. So its life is fixed. Whereas in case of fuel cells, the life is long because as long as we are supplying the hydrogen and oxygen to the system, so it will keep generating electricity. Okay. And even if it is a reverse rechargeable battery, we need to recharge the batteries, whereas in case of fuel cells, no such charging is required, right? And we have seen that the major fuel which is used in these fuel cells are hydrogen. We have seen that in place of hydrogen, hydrocarbons also can be used, and any hydrogen containing chemicals also can be used, but they all need some additional setup which will generate first hydrogen, then the actual fuel cell will function. Okay, so in a fuel cell, This hydrogen is the fuel, oxygen is the oxidant, and in case of hydrogen, we supply this hydrogen to the electrode, a negative electrode, which is anode, and that's why since we are supplying the fuel to this electrode, it is also referred to as fuel electrode. Whereas when you are supplying oxygen to the positive electrode, which is cathode, so that is called as oxidant electrode. Okay, and we have seen that the byproducts when we are using hydrogen as the fuel is the products are we are going to generate electricity, along with it some heat and water vapor are produced. Okay, whereas and there is no SOx or NOx formation when we are using this hydrogen as the fuel. What if we are using hydrocarbons like any CxH2x or CxH2x plus 2 or CxH2x minus 2? So there, since C is there, C plus O2, CO2 formation is going to be there, right? And along with it, we are going to have heat also, right? So that is the difference when you use different fuels. And what about the byproducts at the anode side? Since oxygen is there, and if you are in place of oxygen, if you are using any air, if you use air as the oxidant, we know that the air contains nitrogen and oxygen in fixed ratio, right? So whatever is the nitrogen, so the same nitrogen will be present in the exit stream also, because nitrogen is inert, it is not being used in the system, right? So that way in the anode side, when air is used, nitrogen will be present in the exit stream or flue gas that is coming out, the exit stream, right? And with respect to the efficiency, we are going to discuss about the thermodynamics of it later. So it is possible to achieve practically 50% efficiency and around 0.7 volt is possible. Okay, and we know the advantages of these fuel cells. We have discussed in detail about it. It will work in silent. Fuel cells are compact, they are durable, and they can instantly release the energy. Once it's switched on, it will function, right? And these fuel cells it doesn't need any charging, right? So this way these fuel cells are more advantageous. Okay, and with respect to batteries, in comparison to battery in terms of energy density, if you look at the significant advantage of this fuel cell, the significant advantage of this fuel cell over the battery counterpart is that it's energy density. You just compare the lithium ion battery or lead acid battery, because these two batteries are widely used in the industry, right? So commercially, lithium ion batteries or lead acid batteries are there. If you look at their energy density, it's around 170. If you are using the hydrogen fuel cell with compressed hydrogen cylinders, then it is going to have an energy density of 240. So that is at least 2.4 times it is better, gives more energy density than the lithium ion battery, right? So that's the thing we can observe it. And similarly, the storage density by weight also you can see. If you are having the compressed hydrogen, it is around 240, whereas that of the lithium ion, it is this thing. Okay. So you have portable power packs using fuel cells can be lighter and smaller in volume. That's what we infer from this graph. Okay. So the portable power packs using fuel cells can be lighter and smaller in volume for an equal amount of energy, particularly if you are using this direct methanol fuel cell. We are going to discuss that in detail later. So for this comparison between lithium ion battery and direct methanol fuel cells, we are seeing that it is going to be lighter and smaller in volume if you use hydrogen fuel cells in comparison to lithium ion battery or lead acid battery. Okay, so it's this weight energy density is for the fuel tank. Okay, and that is the reason these hydrogen fuel cells are viable, cost effective solutions for material handling equipments. Okay, so that's why it allows for rapid refueling, it provides constant power during the usage, it eliminates the needs for a space for a big battery storage and the kind of charging you need, the kind of setups, all that are not needed. So that's why it finds usage in small power units like this, whatever you see here in this diagram. So these fuel cell forklifts are in place today. You can see that they are all run with fuel cell powered one. Particularly this Chicago based Central Grocers, they announced the purchase of 220 fuel cell lifts from Plug Power Company in 2008, Similarly, the Defense Logistics Agency is also beginning a 3-year fuel cell forklift pilot project that will place around 100 fuel cell lifts in 4 distribution centers of the company. Okay, so that way there is a widespread acceptance of using fuel cell forklifts and fuel cell lifts kind of thing. This one. And coming to the operation principle of the fuel cell, we have seen a video. I will play it again also. So what is happening? We are going to have a 2 electrode, anode, cathode. In the anode, we are supplying the hydrogen. We have a cathode, we supply the oxygen, and it is separated by a electrolyte, and we have some. What is happening when these fuels are being continuously supplied? The electrons are flowing through the external circuit. The H plus, that is the reaction is taking place. Hydrogen becomes H plus, and electrons flow through the external circuit. So these H plus ions will be moving across the electrolyte and reach the anode side. So where oxygen, H plus ions, and these electrons which are reaching from the external circuit combine to form water. So water is formed as the byproduct. Okay, so that's what happening in this the fuel cell. And we have seen that this fuel cell can be used in combination with because this electricity required to generate hydrogen can be attained through solar cells itself. Okay, so solar energy or wind energy can be used to generate hydrogen. The simple fuel cell same reactor is called as electrolyzer if it is used for water splitting reaction. So there we produce the hydrogen, and that hydrogen is stored safely before used in the fuel cell when it is demand. So this is done when the solar power plant or wind power plant, they generate electricity which are in excess to the demand of the public. So when it is excess energy is produced, that time it is better to store the electricity in the form of hydrogen. Okay, so we convert it into hydrogen, then the hydrogen is again converted to electricity on demand. Okay, when the production in the solar energy and wind energy is less, and that is an increase in power demand, then we will make use of that hydrogen generator to run the fuel cell and get the electricity. Okay, so that will be supplied to the public. Okay, so that way it can be combined with any other power plants which we have discussed in the previous lecture. So we have seen the overall reaction is simply H2 plus half O2 becoming water is the overall reaction. But you have the half cell reaction, because since it's an electrochemical reaction, we have a half cell reaction at the anode and a half cell reaction at the cathode. So hydrogen is getting split into H plus ions and the electrons. So these electrons will be traveling across the external circuit to reach the anode side. Okay, sorry, cathode side. So coming to the half cell reaction taking place at the cathode, as I said, these H plus ions generated at the anode will be passing through the electrolyte and reach the cathode surface. So oxygen is being supplied. So oxygen plus H plus ions and these electrons will combine to form the water molecule, which is the byproduct. Okay, and remember this reaction is endothermic or exothermic. We will have to get back to our basics of what is the water electrolysis. Can you recall what we have learnt in water electrolysis? When water is electrolyzed, we produce hydrogen and oxygen. Okay, so the electrolysis of water under standard condition requires a theoretical minimum of 237 kilojoule of electrical energy. Remember, it is an endothermic reaction. Okay, that means it needs a large amount of energy to be supplied to the system if it is endothermic reaction. We are talking about water electrolysis. So in case of water electrolysis, to water, if you supply energy, electrical energy, so when you supply energy, it will produce hydrogen and oxygen. That's why it is an endothermic reaction. Remember, this reaction is usually conducted from 500 degrees Celsius to even 2000 degrees Celsius range. Okay, so that is the wide temperature range spectrum in which this water electrolysis is being carried out, depending upon the energy input available. Okay, so under standard conditions, so a theoretical minimum of 237 kilojoules of electrical energy is required to dissociate each mole of water into hydrogen and oxygen. Okay, and this is the sum value 237 kilojoule. It is the Standard gives free energy of formation for water, Okay, it also requires energy to overcome the change in entropy of the reaction. So theoretically we need 237 kilojoules, but however there is a lot of change in entropy of the reaction, right? So to overcome the change in entropy of the reaction, the process cannot proceed below the practically below 286 kilojoules per mole if no external heat or energy is added into the system. Okay, so that way each mole of water will require 2 moles of electrons, and given that Faraday's constant is F, which represents a mole of electrons of 96,485 coulomb per mole, it follows that the minimum voltage necessary for electrolysis is about 1.23 voltage. So we have to supply 1.23 volt to affect the water electrolysis. And remember, if it is at a standard temperature, if the electrolysis is performed at a higher temperature, this voltage will reduce. Okay, so that is what happens in case of water electrolysis. So this gives free energy, which we are talking about, which represents the minimum work necessary for the reaction to proceed. And the reaction enthalpy is the amount of energy that has to be provided so that the reaction products are at the same temperature as the reactant. So that means what? It is standard temperature for the values given above. Okay. And now you think about fuel cell. It's the reverse of the water electrolysis. Can you now explain what is happening in case of fuel cell? So what is the chemistry behind this fuel cell thing, and what is the thermodynamics behind it? Okay, so that we will discuss in detail also. You give a think over, you please think over what happens when the reaction is reversed. So we already know about this. What happens during the water electrolysis, because in 8th standard onwards we have been studying about this electrolysis, right? So now what happens when the reaction is reversed? So is it endothermic or exothermic? Or whether how much voltage is theoretically possible to produce? From this, all this can be inferred. Anyhow, we will discuss that in detail again. Just go through it. Okay, so coming to the classification of fuel cells, we have seen that we have, if you look at the different parts of a fuel cell, different components that are present, we are supplying fuel, which is hydrogen, or it may be a hydrocarbon. Okay, and we are supplying oxygen or air, so which is oxidant. So we supply fuel, we supply oxidant, and we will be having anode, we have cathode, we have electrolyte present in it, right? So based on what type of electrolyte is being used, we can classify the fuel cells. So based on the type of electrolyte that is being used, we can classify the fuel cells. Okay, so we are going to look into what are the different type of electrolyte that are being used. Okay, so based on electrolyte, we can classify the fuel cells. Okay, and we have seen that different type fuel, what is the fuel, what is the oxidant, what is the fuel, what is the oxidant. So based on that also we can classify the fuel. Majorly we are going to use hydrogen or hydrocarbon. Other than that, we can even use ammonia, or you can use biogas, right? So like that we have natural gas, coal gas, different fuel can be used. Okay, so that we have discussed already in detail. So similarly, oxidant, either we may be using oxygen or we may be supplying air. Okay, so that way, so based on that also we can classify the fuel cells. Okay, and depending upon the operating temperature, whether you are going to do it at room temperature or up to 50 degrees Celsius, or whether you are going to do at 500 degrees Celsius or 1000 degrees Celsius. So based on the temperature also we can classify the fuel cells, low temperature or medium temperature or high temperature fuel cells. And nature of the electrolyte, either what is the pH, either it is alkaline or whether it is acidic in nature, kind of thing, or whether based on whether it is solid electrolyte or it is a liquid electrolyte, we can classify the fuel cells. Okay, and there are some application of microbes, okay, or enzymes. If you are using enzyme immobilized membrane anode cathode, so we are going to call it as microbial fuel cells or biofuel cells. So based on that also we can have a different type of fuel cells. So fuel cells can be classified based on the electrolyte used, based on the combination of fuel and oxidant, based on the operating temperature, and based on the nature of the electrolyte, and whether it is biochemical system or not. Okay. So now we will look into the fuel and oxidant. As I told you, if you are using hydrogen, pure hydrogen and oxygen as the fuel, so then we call the system, fuel cell can be called as hydrogen oxygen fuel cell. It's a hydrogen oxygen fuel cell. So that's the major type. Mostly hydrogen is being used, and if oxygen is available cheaply, oxygen is used. So then such type of fuel cell can be categorized under hydrogen oxygen fuel cells. Okay. And there is another type. Instead of hydrogen, we are going to use hydrogen rich gas, or that hydrogen containing gas. As I told you, coal gas, natural gas, all the things. If the hydrogen is more percentage is available in it, so we are going to use hydrogen rich gas, and instead of oxygen we can be using air. Okay, so in that case, such fuel cells are called as hydrogen rich gas air fuel cell. That means, what is the meaning? Fuel is not pure hydrogen, oxidant is not pure oxygen. So in place of hydrogen, we are using some hydrogen containing gas. In place of oxygen, we are using air. Okay. And there are other type where we are going to use ammonia as the fuel. So in that case, ammonia air fuel cell. So as I told, ammonia, if ammonia is being used, N is present in the system. So we are going to have NOx products coming out in the final thing. So which we will discuss in detail later. You should be able to know what is the reaction taking place, right? So we can use ammonia as the fuel. So what will happen is ammonia will first form hydrogen. That hydrogen will be entering into the fuel cell anode. Okay. So that way in the system NOx products are formed. Okay. And there is a possibility that in place of hydrogen we can use synthesis gas air fuel cell, right? So that way, what does it mean? We are using synthesis gas as the fuel. And if you are using hydrocarbon, we have hydrocarbon air fuel cell. So hydrocarbon can be used in gaseous form or liquid form. So like that we can keep writing different set of fuel and oxidant combination to give examples for classification of fuel cell, classification of fuel cell based on fuel and the oxidant combination. So when you classify the fuel cell, so what you write is fuel, what is the oxidant used. Okay, like that we classify them. As I told you, based on the operating temperature of the fuel cell, we can classify them as low temperature fuel cells, medium temperature fuel cells, high temperature fuel cells, and very high temperature fuel cells. Remember, we have a system, right? We have anode, we have cathode, we have electrolyte, right? And in the electrolyte, we are going to have membrane electrolyte, or we are going to have acid electrolyte, or we are going to have alkaline electrolyte. Okay, so some membranes, no, they may be operating under optimum conditions of certain temperature range only, right? So we need to have a special membrane for we need to have a special membrane for high temperature applications. So that way when PEM cells are there, we can apply them for high temperature applications. So with the invention of this membrane fuel cells, PEM fuel cells, high temperature applications are coming into picture. And with the invention of new materials, advanced materials, so we are able to use for high temperature applications like solid oxide fuel cells are there. we are going to discuss them in detail. So solid oxide fuel cell, molten carbonate fuel cells are there, so which can operate at very high temperature. Now, coming to type of electrolyte. Based on the type of electrolyte, we can classify the fuel cells as phosphoric acid fuel cells, where the electrolyte is acid, phosphoric acid. And if the electrolyte is alkaline, like KOH, okay, so that way you have alkaline fuel cells, okay. And if polymer electrolyte membrane is used, or proton exchange membrane, that's a membrane is being used, so that is called as solid polymer electrolyte membrane fuel cells, or polymer electrolyte membrane fuel cells, or proton exchange membrane fuel cells. All three represent the same, okay. And as I told you, if molten carbonate is there used as the electrolyte, so we can call it as molten carbonate fuel cells, and solid oxide is used, solid oxide fuel cells, okay. So here these are the 5 different type of electrolytes which are being employed in the fuel cell application. In most of them are in commercial stage also, okay. And these electrolytes, we should again classify them based on the nature of the electrolyte, okay. So based on the nature of the electrolyte, we can call them as, which is like pH. Now if you know the pH of the solution, if it is liquid, among the liquid electrolytes, it can be a neutral electrolyte, or it can be an acid electrolyte, or it can be an alkaline electrolyte. So based on the nature of the electrolyte, based on the pH of the electrolyte, so we can call it as acid fuel cells, acid electrolyte fuel cells, alkaline electrolyte fuel cells, or neutral electrolyte fuel cells, okay. And what about these biofuel cells? Biofuel cells is there are either we can use microorganisms or enzymes. So that we will discuss in detail later. Okay. So based on that also, biofuel cells, non-biofuel cells or non-biofuel cells. So under the biofuel cells, it can be either microbial fuel cells or enzymatic fuel cells. So that's what we have seen. So based on the type of the electrolyte, we can classify them as phosphoric acid fuel cell, alkaline fuel cell, PEM fuel cell, molten carbonate fuel cell, solid oxide fuel cells. And what is the difference in the mechanism when you are classifying all these different type of electrolytes we have seen, right? You can see the temperature range in which they are being applied. Okay, we have AFC refers to alkaline fuel cells. PA refers to phosphoric acid fuel cells. MCFC refers to molten carbonate fuel cells. SOFC refers to solid oxide fuel cells. Okay, so PEM fuel cell refers to membrane fuel cell, polymer electrolyte membrane fuel cells. So each have its temperature range for its application. Okay, so you can see the temperature range. These PEM fuel cells can be used for 20 to 120 degrees Celsius, or high temperature 160 to 220 degrees Celsius. Remember, membrane may get damaged, that they have their activity, water uptake, all that depends upon the temperature. So that's why it limits the application, temperature application. Okay. If you look at the phosphoric acid fuel cells, they also can be applied between medium temperature of 20 to 120, or 160 to 220 degrees Celsius. And with respect to this alkaline fuel cells, they are operated between 60 to 120 degrees Celsius. Molten carbonate fuel cells can be operated at 600 to 650 degrees Celsius. whereas the solid oxide fuel cells, which are mainly designed for using other than hydrogen as the fuel. So there will be hydrogen containing gas, all these are being used. Okay. So accordingly, you are going to have nitrogen will be present in the system, and if air is used, the excess air will be used. So there will be unconverted oxygen being present in the system. Okay. So that way, if you, this is only a hypothetical diagram where we try to compare all the fuel cells, all type of fuel cells in single diagram. Okay. And if you look at the ions which is passing through the each type of fuel cell, that is important to know. So in case of membrane fuel cells, it's hydrogen H plus ions which is passing through the electrolyte. What is the ion? Either it is anion or cation passing through the electrolyte. So that we should know as the basic thing. Okay. So in PEM fuel cell, H plus ions are passing through the electrolyte. In phosphoric acid fuel cell also H plus ions are passing through the electrolyte. Whereas in alkaline fuel cell, it's not the H plus ion will be passing through the electrolyte. It is OH minus ions will be passing through the electrolyte. Accordingly, we are going to have different reaction taking place at the anode and the cathode, which you should able to explain in detail. Okay. And in case of molten carbonate electrode, it is the carbonate which is ion which is being passing through the electrolyte. And whereas in solid oxide fuel cell, it is O2 minus which is passing through the electrolyte. So accordingly, we are going to have different reaction for each type of fuel cell. So it's, even though the overall reaction is H2 plus O2 giving water, which is exothermic and which is producing electricity. So we are having different ion transport taking place in each type of fuel cell, and the direction of the ion transport is also varying. You can see in case of bottom two, so in these two only, the direction of ion is from anode to cathode. So we have anode, this side to cathode sides, the ions are passing. This H plus ion is passing from anode side to cathode side in case of first two type of fuel cells in this diagram, which is phosphoric acid fuel cell and PEM fuel cell. Whereas in case of alkaline fuel cell, molten carbonate fuel cell and solid oxide fuel cells, the ions are moving from the cathode side to anode side. Okay. So what is the ion that is passing through? You can see here. Okay. So you should be able to write what is the reaction taking place in each type of fuel cells. Now we are going to discuss in detail about each type of fuel cells. Okay. So we will discuss them in detail about each type of fuel cell. We should know where each one has its own application range. Okay. So for example, for portable electronics and all, we have direct methanol fuel cell, PEM fuel cells are preferred because we don't want to have a heavy weight. Membrane means it's lightweight, right? So in place of acid fuel cells or phosphoric acid fuel cells or molten carbonate fuel cells or solid oxide fuel cells, their weight is more. So it is preferred that PEM fuel cells like direct methanol fuel cell and PEM fuel cells, they are preferred in the portable electronic applications. Even in car, boats and spaceships where the space is a constraint, we prefer these PEM fuel cells or alkaline fuel cells. Okay. So where we want more efficient and reliability and the space is not a constraint like domestic applications, we prefer these AFC and phosphoric acid fuel cells, alkaline fuel cells and phosphoric acid fuel cells. And in case of distributed power generation and buses, we prefer these molten carbonate fuel cells and solid oxide fuel cells, which is efficient emissions and less noise is there. Okay. So in this type of fuel cells, there are certain fuel cells which can internally reform the methane. That is C fueling section we are going to discuss. So which can internally reform, that is steam reforming can be done. That is in this among these different type of fuel cells, molten carbonate fuel cells and solid carbonate fuel cells are capable of internally steam reforming the methane. Okay. And you can see the temperature range for high temperature applications, molten carbonate fuel cells and Molten carbonate fuel cells and the solid oxide fuel cells are preferred for high temperature applications. Okay. High temperature application means high temperature operations. Okay, operating temperature is very high. So where we cannot have in our car this much degree Celsius operation, right? So they are mostly used for either big bus is there, in that place we can have. Otherwise it is for stationary applications. Okay, it's like buildings, things we can use this high temperature operating fuel cells. Okay, and you can see the power range here. You can see that it's for small power range from watts to kilowatts to megawatts. You can see the range, and remember they are modular in nature. So what is the charge carrier? You should know, we have already discussed in the previous slide. Okay, so they all summarize. So this is easy to remember when you compare and learn. Okay, so now anyhow we are going to discuss in detail about each type of fuel cells. To start with, we will discuss about phosphoric acid fuel cells. Okay. Well, to start with, we'll discuss about the phosphoric acid fuel cells. So this is the why I am starting with phosphoric acid fuel cell is it is the first fuel cell, first type of fuel cell to commercially available, or which has crossed all the obstacles and became a commercial available electric power industry. So this is the first one. Okay, so this is you can call as first generation of modern fuel cells. So phosphoric acid fuel cells, they are considered as the most advanced fuel cell after alkaline fuel cell, and these phosphoric acid fuel cells generally operate at a temperature range of 150 to 200 degrees Celsius. And what is happening in a phosphoric acid fuel cell? As you know, hydrogen is the fuel, oxygen is the oxidant, electrolyte is phosphoric acid. That's why the name, right? So phosphoric acid fuel cell means phosphoric acid is not the fuel, phosphoric acid is not the oxidant, phosphoric acid is the electrolyte here. Okay, if that is the electrolyte, acid is the electrolyte, so easily we are going to have H plus ion passing through it. So that means H plus ions are moving from anode to cathode. Okay, so what is happening at the anode? At the anode side, hydrogen gets split into H plus ions and electrons. So these electrons will be passing through the external circuit, which is felt as the EMF generation. Okay, so then we have at the anode side, coming to the cathode side, we have 0.5 oxygen plus 2 H plus 2 electrons combined to form water, and that is the reaction taking place at the cathode side. Okay, so the overall reaction is H2 plus half O2 becoming water. Okay, so again I am just playing the video again in lecture number 1 itself. I have played you this video. So what is happening in any fuel cell? So we have the hydrogen and oxygen combined to form electricity. How it is formed? So we have gases are entering from both ends. So we have anode side, we have electrolyte, in this case let us say phosphoric acid. We have a cathode side, and water is leaving as a byproduct, there is an exit product. Okay, so when hydrogen is entering the system in the anode side, so they get absorbed at the surface of the anode, and where they get this electrons are separated and going through the external circuit, and H plus ions will be passing through the electrolyte and reach the cathode side. So we have H plus ions and oxygen has entered, and electrons through external circuit has reached the cathode. So their water molecules are formed, and these water molecules are leaving the system. Okay. So this is what happens in a typical fuel cell. In this case, we have considered the electrolyte to be phosphoric acid. Understood? That's what we have been writing as a equation, chemical reaction, all that. Okay. I hope this visualization helps you to understand that thing. Okay. And what about this phosphoric acid fuel cell? Why I started this? Because this is the first one to come commercially available. If you look at the two US manufacturer, major fuel cell manufacturer, what technology they are using is one of them, fuel cell energy company, they use molten carbonate technology, that is molten carbonate based fuel cell, and they produce power plant of sizes 300 kilowatts, 1.4 megawatts or 2.8 megawatt size. Okay, and there is another company, UTC Power, where they use this phosphoric acid technology. When I say phosphoric acid technology, they use phosphoric acid based electrolyte. Okay, so that way they have shown a power plant of size 400 kilowatt. Okay, so that is the range in which these two are the major US manufacturers of the fuel cells, and they are still using these technologies, molten carbonate technology and phosphoric acid technology. Okay, that's why we started with this phosphoric acid, which is at low temperature applications. Okay, so we have seen with the image also I have shown you what is happening. So this can be operated at a temperature range of 120 to 200. You can say around 180 degrees Celsius. So here the electrolyte is the liquid phosphoric acid. They are not kept as a liquid directly. They are kept inside a silicon carbide matrix. Okay, so it's like a silicon carbide material. What you call, we can say that it is saturated with phosphoric acid. It is like, we say, when I say water is saturated with sugar, what we say, in water we keep adding the sugar and we get saturated, means what, further addition only precipitation of will be there at the bottom, right? Same way we are saturating this bonded silicon carbide matrix, so in which we saturate this phosphate with dipping it in a phosphoric acid. So this liquid phosphoric acid in a bonded silicon carbide matrix is the electrolyte. So that is the advanced thing done at a later stage. Okay, just to make it compact. Okay, and we use a finely dispersed platinum catalyst supported on the carbon, and as I said, it can be operated around 180 degrees Celsius. And the efficiency, if you talk about the electrical efficiency, it is relatively low, but overall efficiency is 80% if the heat recovery is done. That is, the heat is generated as a byproduct, right? If you are able to use it for any other applications together, so the overall efficiency can be increased to 80%. And they have been finding applications in the range of 100 kilowatt power generation to 400 kilowatt power generation. And mainly they are used in stationary applications. Okay, so these fuel cells generally use liquid phosphoric acid. We can say that phosphoric acid is kept contained in a silicon carbide matrix, which is placed between the electrodes. So always it's like a sandwich. Electrolyte is the sandwich between your anode and the cathode. Okay, remember these electrodes are generally made up of carbon paper coated with finely dispersed platinum catalyst, and they are even bonded with the Teflon. And hydrogen or any hydrogen containing gases which may be produced from any alcohol or hydrocarbon. Even hydrocarbon is used as the fuel, whereas mostly oxygen or air is used as the oxidant in this type of fuel cells. And the catalyst strips the electrons of the hydrogen rich fuel at the anode. We have seen in the video also. So these positively charged hydrogen ions will be migrating through the electrolyte from the anode side to the cathode sides, and these electrons that is generated at the anode will be traveling through an external circuit providing the electric power and reach the cathode. Remember, it generates only DC power. So always whenever you use this type of power units, there will be AC to DC to AC conversion needs to be there. Okay, converter will be there. At cathode, the electrons, hydrogen ions and the oxygen will react together to form water, which will be discharged as the byproduct. Remember, in spacecrafts, this water is used for drinking purpose. That much pure water is produced in the electrochemical method. Okay. So if you compare the phosphoric acid system, they are almost always fueled by hydrocarbons, which will be undergoing some sort of fuel processing to release the hydrogen gas that reacts at the anode. Usually we call it a steam reforming kind of process. These phosphoric acid fuel cell systems, we can tolerate, it has a tolerance to CO2, because even when we are not using hydrogen as the fuel, when you use this anything hydrogen containing gases, so CO2 formation may be there. So that tolerance to CO2 is okay with this type of phosphoric acid fuel cell, and even it can tolerate unreacted hydrocarbons also, because we cannot say that 100% conversion of the hydrocarbon into hydrogen takes place in a system, right? And this acts as diluents to the fuel, and the concentration should be minimized. CO gas, however, will poison the platinum catalyst at the concentrations, if it is the concentration is more than 0.5 percentage. So that is the one issue we have. CO gas formation should be avoided if you are not using hydrogen and using any other hydrocarbons. Okay, so that is the thing. And if you look at the flip side, we have seen that CO should be removed during the processing, because if you allow the CO to be present enter into the fuel cell, so that will poison the platinum catalyst and deactivate them. Okay, so that is the concern associated with using hydrocarbons. Okay. Coming to the next fuel cell type, alkaline fuel cell. We have seen acid type of fuel cell, which is phosphoric acid fuel cell. Coming to the another nature of fuel electrolyte, which is alkaline in nature. So we have alkaline fuel cell. Remember, this is the first fuel cell to be developed. We have discussed in the previous lecture number 4, where we have discussed the history of fuel cells. We have seen fuel cell pioneer F.T. Bacon, who generated the first fuel cell, alkaline fuel cell. So you can see him posing with this fuel cell generator, which is a 6 kilowatt fuel cell stack, which was prepared in 1959. And even the Apollo fuel cell systems, where you can see the n number of fuel cells, which is arranged as a stack, okay, which is used in Pratt and Whitney aircraft engineers. Okay, so this is the first alkaline fuel cell, which was prepared by British scientist Francis Bacon. He used 45% potassium hydroxide. He also introduced the gas diffusion layer concept into these fuel cells. So what is gas diffusion layer? It will provide a increased surface area at the gas electrode electrolyte interface. And remember, among the different alkaline hydroxides, we preferred KOH because it showed more conductivity. And oxygen reaction at the cathode of the AFCs will occur more quickly than in an acidic electrolyte. So oxygen reaction that is taking place at the cathode side will be occur faster rate than acid fuel cells, acidic electrolytes. Okay, so that way we see higher efficiency for a similar cell conditions. These alkaline fuel cells will provide more efficiency, higher efficiency. And remember, it also allows the usage of non-precious metal catalysts such as nickel in place of platinum. Okay, that way in comparison to acid catalyst, because when you say acid, highly corrosive nature, we have to use some precious metal as the catalyst. So when you go to this alkaline range, so it allows to use some low cost catalyst also, thereby the overall cost can be reduced. Okay, so that way we can see the nickel oxide cathode and Bacon cell, which operate even at the temperature and pressure of 205 degrees Celsius and 40 atmosphere. They were constructed using simple nickel electrodes. Okay, so in 1959, a 5 kilowatt fuel cell stack was unveiled by him. In 1950s, the technology also being picked up by a number of companies, including Alice Chalmers Manufacturing Company. One of these companies' engineer, Henry Eric, he built a 15 kilowatt fuel cell stack of 1008 cells based on alkaline fuel cells and used it to power a tractor. A tractor was run using a 15 kilowatt fuel cell stack. Okay, so that was the development in 1950s, which was alkaline fuel cell. That company continued to research into this technology, and they even built a golf cart. You know that high class people play golf, so there you will have a golf cart where they used to take the bat, all the water, all the things in a cart, right? So that cart is called golf cart, which is also they used it in a submersible one, or even they used in forklift truck. They all being powered by fuel cells, mainly using this alkaline fuel cells first. Okay, and that time another company, Union Carbide company, they were also investigating the technology and developed a carbon gas diffusion electrode. That time only these gas diffusion electrodes were generated. Okay, and that work has helped to develop fuel cell powered radio and the fuel cell motorbike for the US Army. Okay, so that way, so these alkaline fuel cells were used in US Army as well as for powering the radios also. Okay, and remember in 1970s, the International Fuel Cells developed a more powerful alkaline fuel cells, mainly for the Space Shuttle Orbiter. I have discussed this in the history of fuel cells itself. So they used 3 fuel cell power plants to supply all of the electrical needs during the flight. They didn't even have a backup battery on the space, right? So practically, which means that the efficiency is greater than 60% was there, and also they believed that its functioning was such reliable. They didn't even have any alternative backup plan for having energy. Okay, so that was the efficiency with which these fuel cells are working. Okay, so and in spite of high efficiency reported, this development of alkaline fuel cells, they had some limitations. They were hampered by the reactivity of the alkaline electrolyte with the CO2 from the air. See, air contains certain ppm levels of CO2, right? So that lead to the formation of carbonates, which had the probability of poisoning the fuel cell. So that is the concern, because we are supplying air into air as the oxidant, right? So air contains certain amount of CO2. That means that when you are using KOH as the electrolyte, so that poisoning of CO2 is a concern. Okay. Another concern is CO formation also, right? So that thing was a problem. So that way, this even though, and then also these cells were used in the space, they were filled with pure oxygen. That's why they did not use air as the oxidant. Pure oxygen is used, but high level of purity needed makes terrestrial use of pure oxygen expensive, because at terrestrial level getting pure oxygen means that you know the cost involved in it. Okay, so that is the thing. So that to summarize the points of these alkaline fuel cells, so it is the oldest of all the fuel cells that have been generated so far, and the electrolyte used in this alkaline fuel cell is an alkaline, mainly KOH, and the operating temperature is around 60 to 90 degrees Celsius. It's a low weight alkaline fuel cells. That's why they have been preferred for space and military applications. The anode generally used are because even as well as phosphoric acid fuel cell on here. So the anode is platinum and carbon, and whereas the cathode can be platinum and carbon or silver. Okay, silver supported on carbon. So this, when we say platinum and carbon, it is like 10 weight percentage of platinum supported on carbon. Carbon is activated carbon. Okay, so this activated carbon can be say Vulcan carbon, or even in place of carbon we can use even carbon nanotubes. Okay, so that way in place of carbon we can have carbon nanotubes also as the support. Remember, what carbon nanotubes are costlier than carbon, but the advantage is they have high specific surface area. Okay, so the electricity produced with these alkaline fuel cells are 60% possible, and we can use hydrogen, hydrazine, ammonia, hydrogen peroxide fuel cell, ammonia. It is easily cracked at 500 degrees Celsius to produce hydrogen through the reaction. So even sodium borohydrate can be used as the fuel. So compared with other type of fuel cells, the alkaline variety offered the advantages of high power to weight ratio, and this is primarily due to intrinsically faster kinetics for oxygen reduction to the hydroxyl anion in the alkaline environment, and therefore the alkaline fuel cells were ideal for space applications However, for terrestrial use, the primary disadvantage of the cell was CO2 poisoning of the electrolyte. That's why pure oxygen is being used. Okay. So CO2 is not only present in the air but also present in the reformed gas, the hydrogen-rich gas produced from the reformation of hydrocarbon fuels. And in the poisoning of an alkaline fuel cell, the carbon dioxide reacts with the hydroxide ion in the electrolyte to form carbonate, thereby reducing the hydroxide ion concentration in the electrolyte. So that's why this overall efficiency is being reduced. This is the summary of what we have discussed under this alkaline fuel cell. Okay, so what is the reaction taking place in case of alkaline fuel cells? Remember, it is not the H plus ions that is causing through the electrolyte. That's very importantly we have to note down. Okay, so you can see what is the reaction that is taking place. How cell reactions taking place are, so here mainly at cathode your ORR reaction is taking place. So you have OH plus ions being formed at the cathode side. Okay, so that formed this oxygen plus electrons plus water will form OH minus ion. So that OH minus ion is passing through the electrolyte. Okay, so that's why it is important to note that the ion transport, what is the ion that is being transported across the electrolyte? Ion transporter is OH minus ions, hydroxyl, okay, hydroxyl ion. So that's why then if it is reaching the anode side, what happens? So hydrogen plus OH minus ions will combine to form water plus electrons. So these electrons will be passing through the external side. Remember, whatever it may be the ion transport taking place, only at the in fuel cell, only at the anode, the electrons are passing through the external circuit from the anode side. Okay, so where the water is being produced as a byproduct. So in this case, in case of alkaline fuel cell, water is produced. Here in case of alkaline fuel cell, water is consumed at the cathode side. Here water is consumed. So whatever water is generated, that itself consumed. We need not even supply fresh water. Okay, and water is being produced at the anode side. Okay, so in the anode side, water is the product. Okay, so here it is a reactant. That we should know. Overall reaction is same, H2 plus O4 to giving water, but we should know what is the reaction taking place. So what is happening at the cathode? At cathode you have oxygen and these electrons coming and it consumes water to produce OH minus hydroxyl ions. Okay, so if you balance it, we are going to have 4 electrons and 2 water. Okay, and what thus produced OH minus ions will be passing through the electrolyte. So once they reach the thing, so that side we are supplying hydrogen or hydrogen produced from the hydrocarbon. Okay, so that will give you water as the byproduct and your electrons are passing through the external circuit. Okay, so that is what being taking place as the reactions. Okay. So if you show that again is the reaction taking place, what are the different anode that is possible? Uranium, nickel, platinum can be used as the anode. Cathode can be nickel oxide. So in alkaline fuel cells, generally nickel oxide is used as the cathode. Platinum supported on carbon or nickel supported on carbon is used as the anode. And we look at the advantages and disadvantages associated with these alkaline fuel cells. So it uses the low cost electrolyte, KOH can be used, and there is a flexibility in the operating conditions, and non-noble metal catalyst can be used. Oxygen kinetics is faster in alkaline solution, and thereby there is a reduced ORR losses, oxygen reduction reaction losses, and it has high power densities and short startup time. And some of the disadvantages, as we have discussed already, if you are not removing the CO2 which is formed in processing the hydrocarbon to hydrogen, So there will be carbonate formation in the electrode which may poison the catalyst. Okay, so that's why we should have to use either pure hydrogen and oxygen should be used preferably. And with respect to reliability, it is low reliable and extremely high cost is involved. That's why they are not being used for commercial applications. Okay. And if in the space programs, US space programs, these alkaline fuel cells were used, and they had a lifetime of 2,600 hours to 4,000 to 5,000 hours, so which was appeared to be achievable with the modern terrestrial designs. While relatively short, this is considered sufficient for a power unit in a vehicle, potentially allowing a range of 200,000 kilometers. However, much greater lifetimes are normally required for stationary power applications, and we have to overcome this electrolyte poisoning and the corrosion. They are the main culprits which reduces the operating lifetime of this type of alkaline fuel cells. We can take care of the component corrosion by using a barrier layer or modifying the system design to minimize the contact between the susceptible components and the electrolyte. And dealing the electrolyte poisoning resulting from the presence of CO2 is the major difficulty that we face in this alkaline fuel cells. Okay, the most basic reaction between the two can be shown here. CO2 plus 2 KOH will form this K2CO3 plus water. So that the concentration of this hydroxyl ion is reduced, increasing the ohmic resistance across the cell electrolyte, which leads to the energy losses. Okay, so then the carbonate, which is mildly acidic, which can also reduce the pH of the electrolyte, which will have an adverse effect on the reaction kinetics at the cathode, where the oxygen reaction is taking place. Okay, so that way we have to absorb this hydrocarbonate or CO2 needs to be absorbed using some soda lime absorption or molecular sieve absorbers are being introduced into the fuel cell system to remove the CO2. Because the CO2 is present means this is a disadvantage. That will be consuming the OH minus ions, because KOH plus CO2 will give you K2CO3. Okay. So it is technically possible to remove all this carbonate that has become dissolved in the electrolyte by operating the cell at a very high current density for a short period of time. Otherwise, a circulating electrolyte AFC can either simply refresh the electrode. Okay. Okay, PEM fuel cells we'll discuss in the next lecture. Well, in this lecture number 5, we have discussed about the classification of fuel cells, and we have seen in detail about phosphoric acid fuel cells and alkaline fuel cells. In the next lecture, we will discuss about PEM fuel cells. Thank you so much for joining my classroom. Meet you in the next lecture. Bye-bye.